That means the slope of graphing. The slope on this graph is the second derivative function. So would the slope negative? So that would be here and here. These would be between 1, 3, and between this 3, negative 1. Out of those, also to know where is the first derivative negative, where y values live. Right? This is graph the derivative, and y values the derivative values. So let me put where we have negative slope, negative y values is negative 2, negative 1, 1, 3. So negative 2 to negative 1 and 3. Because derivative and the second derivative are both negative. Those are the bases are the y values, which are the derivative values, and both values, the second derivative value, both negative. The second derivative make it constant down, and the first derivative will always be decreasing. Does that make sense? So then, is that clear? Hopefully not. So then it would be that 1 point for the interval, negative to negative 1, 1 to 1.3, because first derivative is decreasing. This is the second derivative is negative, but etc. The first derivative is decreasing and negative. So first derivative is negative and the second derivative is negative because the first derivative is decreasing. So there we go. So that would be another point. Okay, let's see. Find x-rays of all points of inflection. The graph and give me some answers. So take maximum or minimum occurs in the first derivative is 0 and defined and just find point of inflection anywhere that derivative is 0 or undefined. And you just So question asking us relative maximum, relative minimum. So we're first derivative, we're defined chase on. When the points inflection, that's second derivative. Whereas second derivative is 0 and undefined and just. So in this graph, the slope for second derivative. We're looking for where slope is 0 and just fine. So that would be here at negative 1. That's what horizontal means, slope is 0 there. And slope change for negative opposite. That would be negative 1. And then up again 1, slope 0, and it just from positive slope negative. And then negative 3. Slope is 0 and changes negative slope, positive slope. So negative 1, 1, 3. Because the second derivative is 0 and change sign. Let's see. This is 2 points. One was identifying this value, negative 1, 1, 3. And so they talk about first derivative, but you talk about second derivative. Talk to the first derivative changing increase decreasing, which means the second derivative changing negative, positive, positive, negative. So you would set up further, and they explain a little bit differently, but they'll kind of same way. And the last one. Then the F1 is going to be the initial condition problem. Write in F of x involved in it. So we know that when x is 1, y is 3. Right? Our initial condition here, x1 is 3. So starting off with value 3. We're going to go from 1 to whatever value x1 is equal to of derivative. Right? We integrate derivative to get total into the function. So we know if our function stops at 3 when x is 1. To figure out the change that value, we integrate rate of change, integrate derivative. So from 1 to ever. So that's defined if 4 is over negative 2. That means it's within 4 and then within negative 2. And figure out what these are. So plug in 4 first. Integrate from 1 to 4. I'm going to add the area, right? So I'm going to track the area to negative. Right? So 3 less negative 12. So negative 9. Right? I contrast off at 3 and 1. Right here at 1, 3. And this tells me how much the fund value changes. And this is a graph of the derivative. So this represents change in f. It goes on 12 to area is negative. You can't do that. Sorry. At 1, the value is 3. And it goes down 12. This area is 12. So in f of negative 2, we're only from 1 to negative 2. From 1 to negative 2. But that's going backwards. Right? We're only from right to left instead of to right. So even though this area is below the x-axis, we're going to add it. This is kind of like going in reverse. So we're going to figure out what was it back at negative 2 that made it 3 when we got here. So they subtracted 9 from where we're here to get 3. For us to figure out what it was back, we need to add 9. Right? Just if you go back, you go right to left, area is flip-flopped. Below is positive enough to be negative, so we would add that. Get 12. So let's see what's that pointer. So 1 point for running the integral, 1 point for expression. Oh, okay. So 1 point for the integral part and 1 for the whole thing. So that's really going to point writing that. Then just 1 point for plus 2. So it was negative 9 and negative 9 and 12. Those would be their points. Okay, so just kind of tell you they do repeat these descriptions. It's a very common type question. If you put that into 2014 test, Number C on 24th test is similar to that. We can look at that one in a minute. If you look back at 2012 test, oh wait, 2013. So 2013. 2013 it was 4. 2012 was number 3. So you can see every year is like number 3 or 4. Something like that. And 2011 was 4. So there's a question line every year where they give the graph of the derivative and they ask you questions about function and second derivative. Does that make sense? So keep in mind that when you're looking at a graph of derivative, y derivative values, slope are derivative values, and if you want to know function values, you have to integrate up to the area to get the function they use. Right, the slope derivative, second derivative, y they use. The first derivative here. Oh, let's see here. So this is 22 number. This is another type of one that you'll see every year. You'll have Fremont and all the Fremont table and asking questions about tables. So I'll go tell you which one in the other year like this. So, but we'll get this one. So the table here shows time, minutes, and the water temperature in degrees Fahrenheit. So this is the temperature of water at time T is modeled by strictly increasing twice different voltages per U. So even if you're seeing part of temperatures, they're just letting you know that the temperature is always increasing. There's not a point in where it went down and back up. That's strictly increasing. And twice different voltages that are sensitive derivatives. So it's kind of like clear. So they're trying to do with weird function or thing. Where D is to measure degree Fahrenheit in minutes. Time equals so the temperature of the water is 55 degrees. The water is stayed for 30 minutes, and it'll show it the first 20. Begin time equal. Value W gets the time for this 20 minutes you're going to take above. So this is the data table to estimate W prime of 12. Computations of each answer using unit and treatment of your answer in the context of this column. So 12 is to be between 9 and 50. And W prime of 12 means the derivative of W12. Now you're trying to fit a derivative from a table. What you're going to use is slope formula, right? Because the derivative means slope. If you don't have any equation or a graph to find the exact slope from, if you look at a table, and we just estimate slope using slope formula. So we would do y2 minus y1 over x2 minus x1. We would slope formula. Right? Slope is the way to calculate a derivative. Right? There's an x for line, just line constant slope. So you find the derivative of a line, choose slope. But if you have approximate slope rather than substance, you still use. So this would be our y, 67.9 minus 61.8 over our x is 15 minus 9. We're using 9 and because the two values close to the one that is above. It's about 12. 12 is on this rule, so we're going to use two values closest to it. And this is calculator pointing out these calculator the first two problems. That's two problems. If I were to type this in, I would get 6.1 over 6. Multiplied with 0.01. And the units would be, right, the units would be the units y over the units of x, because we did the change in y of change x, would be degrees Fahrenheit per minute. This would be the rate of change of the temperature. Rate of change of temperature at D equals 12. So every year they're going to approximate a derivative in the tool. And when you do them, you see on a single of them. And it's one of the things they could do. That just means you use the formula. I'm going to want to show you put into the formula and make you include it. And they may or may not interpret it, but most of them they will. So let's see. This is a 12. Pull it up here real quick. So on 2012 test, 1.4 the estimate, 1.17 or 0.06. The water temperature is increasing at over approximately whatever minute at T equals, let's say. So the rate change of water temperature. Right. Part B, use the data in the tool to evaluate an integral from 0 to 20 W prime T. Then correct and interpret mean from 0 to 20 of W prime T. So just W prime, that's the derivative W. If I integrate the derivative of W, I'm getting W. Right? Because we're a derivative and integral, they cancel each other out. So basically, this is you integrate the derivative W, you'll get W. And you put top number minus the bottom number. So we would W of 20 minus W of 0. Which would be 71 minus 55. Which would be 60 degrees Fahrenheit. And when you integrate the rate change, which is what the derivative is, the rate that the water temperature is changing, you get a total change, right? There's a total change in the temperature of the water from the first 20 minutes. So you integrate the derivative, you get function, and we have function value table here. W of 20 is 71, and W of 0 is 55. You subtract what you find is the total change in the temperature of those 20 minutes. We get 15 degrees Fahrenheit, and this is the total change water temperature from T equal to 0 to equal to. So if you integrate the derivative, get the function. The main thing you need to know there. So this one is worth point. 1 point getting 16, and 1.4 saying water temperature has changed 16 degrees from 0 to 20. 16 degrees when it was. Alright, part B, 0 to 20, the average temperature of the water in tub is 120. The integral 0 to 20. That's the description, right? So the average, which are going to divide 20 to 20. You left 3 months out of 4 intervals and give out data table to approximate this. As the approximation, estimate or underestimate the average temperature of water for these 20 minutes. Alright, so we use the left 3 months to calculate this integral. So we're going to do 0 to 4, which is the width of 4. 4 to 9, which is the width of 5. 9 to 10, which is the width of 6. 15 to 20, which is 5. And we're going to do last one, so we use the high and the left. So we're going to do 4 times 55. 4 times 55. 5 times 51.1. 6 times 51.8. And 5 times 57.8. So we're going to 12.8. We'll use the 3 months down. So 1/20 of 12.8. If I do 4 times 55, 5 times 57.1, 6 times 60, 8, 5, 6, 7.9. Add those all by 12.8. And so I'm doing average temperature. I have to divide that by 20. Or divide by 20. And I'm going to get 2.79 degrees. So that's the approximation overestimate or underestimate the average temperature. It's going to be an underestimate. And the reason is because the function that we're working with is strictly increasing. If I use the left arm on increasing function, if you imagine what it looks like it's increasing, it looks something like this. If I use a left arm, I use the height of left to draw a rectangle, all we're going to be drawing a thing that is under the curve. There's always going to be not enough area. It's increasing. It's an increasing function, you use left arm, then any approximation unit will be under limit. If it's increasing and you use the right arm, then any approximation unit will be over limit. And then it's the opposite for decreasing. If it's increasing, left arm would be too much, this arm would be not enough. So it's going to be under limit. Left motto. Always underestimate. In the control. Alright, so then part D, it says for 20 to 5, that's 5 minutes after the end of the table. The function W that knows the water temperature has first derivative given I and the description. Based on model, temperature of water at time equals 25. So we know that after 20 minutes, water temperature is 70 degrees. So we're starting off at 7 degrees. And if I integrate from 20 to 25, because it's 71 degrees at 20 minutes. Now I want what it's going to be at 25 minutes. So I'm going to start 1. That's the start I either have. And I'm under 25. And we integrate the rate of change, the total change. So we integrate this function here, rate of change in. That's the water temperature changes in the next 5 minutes. So we use it. Let's see, we're going to. We are going to type in C1. And the integral, there's a couple places you can find. I'm going to go to menu and calculus. It's 2. Or if you go to menu, in the very bottom row, it's second from the bottom. So you go to 25. So 25 of 0.4. The root of, use the steer f equals to cosine 0.06 t. If you don't get it, maybe your calculator on any of this. I'll make sure both of them they're all set gradient. You don't need to agree with like it's not set to the mode. Go to document. Yeah. Press the box here throughout the key and notice these is that it's saying region. Oh, okay, I think it's again. Then I have the answer. Maybe it's what a note in my things or on those. Depending, 84 times not right. Did you have any 3.42? Oh, let's see. I'll make sure they're right mode, or the 80 exam, but the one in rating mode, so it would be, I actually had wrong here. Apparently I'm not going to agree. Even the anti-limit, 3.043.